Last we discussed was preparation reactions. Now let us discuss about chemical reactions of carbonyl compounds. To understand what type of reactions that take place, so first you need to understand the structure, how it looks like. Typically, an carbon oxygen bond should be like this, okay, with a pi bond forming here, correct? But due to the strong electronegativity of oxygen, now the carbon oxygen bond will have orbital forming, orbitals cloud would start becoming like this. This is the way the orbital cloud will start pushing up, which means the oxygen will occupy most of the electron cloud and carbon will have scarcity in the electron cloud, which means this will develop delta positive charge and this will develop delta negative charge. Is it making sense?
Yeah.
Moreover, if you notice the carbon oxygen bond here, if this is how the sigma bond, pi bond is forming between these two, this is a pi bond, let's say, correct? This is the pi bond. Then you will notice that there will be a pi star orbital which will be present like this. Okay, this will be the pi star orbital, correct?
Yeah.
And these are the two bonds, correct? And due to this pi star orbital present here, correct? Now what happens whenever a nucleophile try to approach here, okay? So if a nucleophile is supposed to approach, nucleophile has to first approach through pi star to convert that into pi. Understood?
Yeah.
But while nucleophile is coming, this angle is not exactly 90 degrees to this, correct?
Mm.
So which means if you have two groups on carbon like this, these are the two groups present on the carbon. Nucleophile doesn't have to approach like this. It has to approach somewhere like this. Are you
Okay.
are you
Okay.
getting
Yeah.
the sense now? So
Yeah.
it cannot come
Diagonal.
directly from the top here. It has to come with an angle here. Okay.
Okay.
So which means it is not exactly 90 degrees to this this or this bonds here. Okay. That's why the crowding which is present on these two groups strongly affect the nucleophile. Okay. So you will see a strong repulsion between these two. Correct. So which means this will make a steric hindrance. Steric hindrance. Got it?
Yeah.
So due to this steric hindrance, what you will notice here is, okay, uh, two factors, two factors which influence reactivity, that is nucleophilic addition reactions. Nucleophilic addition reactions, that is NAR, includes, okay, delta positive charge on carbon and steric hindrance by groups on carbon. Okay, these are the two factors which will strongly influence. Is this clear, beta?
Yes, sir.
And you see there are two types of mechanisms that will usually happen. First mechanism, that is mechanism 1 for NAR, that means nucleophilic addition reaction. First is, suppose if you have C double bond O and I have an electrophile nucleophile combined together like this, okay? Then the reaction could happen such a way that oxygen's lone pair can attack here. Then we will get here this way with positive charge coming here, okay? And thereafter the nucleophile will go attack here, and that's how you will get oxygen electrophile bond and nucleophile getting connected. In this case, the rate determining step would be the second one. This is first type of mechanism. The second type of mechanism includes, for nucleophilic addition reaction, will be double bond O with nucleophile directly attacking first. So in this case, electrophile is not present first. First nucleophile is present, and that will create an O minus and nucleophile. Thereafter, an electrophile is been attached here. Okay. In both the cases, the second step is the rate determining. First nucleophilic addition is the rate determining step. Okay, beta.
Yes,
So,
sir.
so it doesn't matter whether you make an acidic medium or basic medium. The rate determining step will always be the nucleophilic step.
Okay.
Let me show you with an example here. Suppose if I put an example here. So let's say I have an acetone type of a group, and then I'm doing H plus and hydrolysis like this. Okay. So which means first I'll add H plus here. So on adding H plus, first I'll get double bond OH plus. This is an electrophilic addition. Thereafter, let's say a nucleophile like alcohol is been added. So nucleophile will attack here. This bond will shift here. And you will get a product like this, OH and OR plus H plus. Got it?
Yeah.
And again, like I said, this is the rate determining step. Clear?
Yes,
So
sir.
if I write the overall reaction would be like this, where you will have C double bond O, and this is H plus and ROH, and you will get a product as OH and OR. Okay. So first electrophile to be added, next the nucleophile should be pushed. If I have second example where nucleophile is added first, like RMGX for instance, this is minus and plus. Okay. Now what would happen is, because there is no electrophile present, like H plus kind of group is not present, so the first step itself is a nucleophilic addition. So you will get this as O minus R, and the Mg plus Mgx plus will get associated with oxygen. This is going to be formed, and this, if you treat with H2O, now O minus can take H plus, and magnesium can become X and OH. Okay, this is what is the product that you will get. So if I write the overall reaction now, will be equal to C double bond O in the presence of R dash MgX with H2O. So that would be OH and R dash. I mean, if at all I take R dash, that will be R dash. Okay.
Okay.
So basic idea is clear, beta.
Yes, sir.
90% of the reactions in aldehydes and ketones are only these. That is either an
Okay.
electrophilic addition first and followed by nucleophilic, or first nucleophilic then followed by electrophilic. So you need to
Okay.
just judge whether it is in an acidic medium or a basic medium. In acidic medium, how the mechanism takes place. In basic medium, how it will happen. Okay? But
Yeah.
that's the major crux of it. Now let's quickly follow through the reactions now. Okay?
Yeah.
So first reaction includes HCN addition. The HCN addition suggests that there are two ways you can proceed. Either you first react with Cn minus and then you react with H plus, or you can add HCN first so that oxygen can take H plus, and because HCN is a very weak acid, it may not be giving sufficient amount of cyanide. Just to increase the cyanide concentration, you add some extra amount of Cn minus. So Cn minus will get added, oxygen will take H plus from here. So what do I supposed to get? I'm supposed to get OH and cyanide of the same carbon. Clear?
Okay.
Right.
Yeah.
So that means this will be cyanohydrin formation. Okay.
Yeah.
This will be cyanohydrin formation. So all aldehydes and ketones give the reaction, as RCHO, PHCHO, P double bond O CHO3. That means all aldehydes, all ketones. There are certain ketones which does not give this reaction. That includes this one, diphenyl ketone and phenyl with this one. Now here is something what you need to learn. What were the two factors which decided the reactivity here? One is the crowding. Second one is the delta positive charge on carbon. Hmm? Combining these two factors, if at all I write the order of reactivity, then this is the order of reactivity. First will be CF3CHO. Although CF3 looks maybe little bulky, but it is strongly withdrawing. Because of
Yeah.
strongly withdrawing nature, carbon will have sufficient or very high delta positive charge, which will facilitate the nucleophile to approach. Is that clear?
Yeah.
So this is the reactivity. CF3CHO, then CCl3CHO, then CF3CF3 on both sides. That will activate carbon's positive charge very heavily. Then
Mm.
comes formaldehyde, then acetaldehyde. That means normal aldehydes are all first. This one, then CH3. As you can see, the bulkiness is increasing. Propanaldehyde, benzaldehyde. Why benzaldehyde is less? Because the pi bond on benzene will resonance stabilize and decrease the positive charge on carbon. Okay. Next comes, very bulky amount of aldehyde. After that comes ketones. Then
Okay.
ketones, basic ketones. Then slowly start bulky the ketones here, more bulkier ketones. Then again, phenyl substituted ketone will be very less reactive. Because of the resonance
Yeah.
which it provides to C double bond O. Okay.
Mm.
And then two phenyls. Later on, one phenyl and one tertiary group. So these all will have very, very less reactivity. Clear beta now?
Yeah.
Right. So this is how you can check it out, that how the reactivity usually is observed here. Okay.
Mm.
Right. Next, second one, NaHSO3, sodium bisulfite. Sodium bisulfite has this particular structure, SO3H, with sulfur having a lone pair. Sulfur's lone pair is much more reactive as in nucleophile compared to oxygen, because oxygen is smaller in size, holds, because of its electronegativity, holds electrons more strongly, while sulfur can donate more easily. So sulfur's lone pair will attack on carbon, getting this product first. Okay, and this will take H plus and gets into this white color PPT. Okay. So this formation of white color PPT suggests that there is a presence of aldehyde or a ketone. Okay. Now this white PPT, if you add it to NaOH, again it get dissolved. That means SO3 will get separated as SO2 here. Na2SO3 will be separated and aldehyde will form. Or even when you add it in acidic medium, this SO2 will come away and NaCl will form and RCHO will be present. So what happened? This got dissolved in both basic medium as well as acidic medium.
Mm.
Got it?
Yeah.
Now you notice this. It reacts with every methyl ketones and aldehydes only. Methyl ketones is an important word here. All aldehydes, no problem.
Yeah.
But when it comes to ketones, I need to have a methyl ketone here. Okay. But yet, you see, phenyl with a methyl or terbutyl with a methyl, correct? These two, even though they have a methyl substitution, yet they will give negative bisulfite test. Okay. The reactivity is extremely slow. So this will not be considered for reactions. These anyway will not give because these are does not have any methyl ketones at all.
Mm.
Clear? So
Yeah.
these are the compounds which you need to check, which will give negative bicarbonate test. Rest all will give positive bicarbonate test. These are all
Okay.
standard integer type questions, beta. Which of the
Mm.
following will give positive, or which of the following will give negative bisulfite test or HCN test, and so on. Okay. Hmm.
Yeah.
In NCRT, this was mentioned that if at all you have an aldehyde and an alcohol together, because both of them are
Mm.
colorless solutions, how do we separate them? This is the best method. Use sodium bisulfate. With sodium bisulfate, the aldehyde will get precipitated, but nothing will happen to alcohol. So on filtration, you can remove the alcohol separately. Then you can, remove the precipitate form separately. And in
Mm.
that precipitate, again, when you add HCl, you will get back your aldehyde. Okay. That's how we can
Okay.
use it for separation method. Yeah.
Yeah.
Next is reactivity with water. Okay. Suppose usually water does not attack directly in basic medium. It is not that easy. I mean, it does happen, but usually acidic medium is more preferable part. So in acidic medium, the lone pair from here will take H plus first, and then water as a nucleophile will attack. So what you will get here is a hydrate of a carbonyl compound. Two OH groups are called hydrates. Hydrate of carbonyl compound. Now in this hydrate, if you notice that water as it attacks here, pi bond is shifting. This is the mechanism which will take place. Now this hydrate will only be stable for two reasons. One, there is less bulkiness around it. Okay, that means this H and R are smaller in size. Okay. Second thing, this OH groups are getting stabilized by some hydrogen bonding. Okay. Like in
Mm.
this case, CCl3 CHO is called chloral. And in chloral, if carbon gets OH and OH here, that hydrogen will get hydrogen involved into hydrogen bonding with chlorine on both sides. This is called hydrate of chloral. This is called hydrate of chloral. Okay. Now there should be some reason for which this group should be stable. Now there is one more reason. Suppose if you have a three-membered cycle here, three-membered cycle you have, if it is sp2, it is extremely unstable form, because
Mm.
sp2 demands for 120 degrees angle, but here it is only 60.
Yeah.
So it has a huge angle strain. How do we minimize the angle strain to convert sp2 to sp3? So you can see bringing two OH groups is actually releasing the angle strain. That's why this is also very stable in its hydrate form.
Okay.
Similarly, ninhydrin. This compound is called ninhydrin. Ninhydrin, when you add H3O plus, here if at all it becomes OH and OH like this. So like this, O and H here, O and H here. So this oxygen and hydrogen will make a hydrogen bonding. This oxygen and hydrogen will make a hydrogen bonding. That stabilizes the hydrate. So this is a very stable hydrate. Okay. So even if
Okay.
you have, diphenyl with, keto groups here like this.
Mm.
So the center carbon's ketone, if at all it gets hydrated, you'll get oxygen here and hydrogen, which will make a hydrogen bonding with the adjacent C double bond. This is also a stable hydrate. Okay.
Okay.
So you can see acetones are highly unstable. Okay.
Mm.
Acetaldehyde slightly stable. If the equilibrium is equal to 1, that means we can consider it to be slightly stable.
Mm.
Formaldehyde is highly stable. Okay. CCl3CHO, which has, chloral, will have hydrogen bonding, so highly stable.
Yeah.
CF3CO, CF3 will have hydrogen bonding on both sides. That's why it is even more stable. Clear? So this is a list of hydrates which are stable forms. Chloral, this propanone, and all of these cases. Close it with love. Yeah.
Mm.
Next, reaction with ammonia. See, aldehyde, when you react with ammonia, okay, there is easy way to understand is this, that you are supposed to remove these two hydrogens and one oxygen, dehydrate them, and convert
Mm.
them into a double bond form. So this double bonded form of carbon nitrogen is called imines.
Mm.
Okay, beta. So you can see how it is formed. Ammonia as a nucleophile can attack, and then pi bond can shift on oxygen. Considering you take it in mild acidic medium, so that means oxygen will attack H plus first. and then ammonia will attack. And then the hydrogen from ammonia will shift on to OH, remove that as OH2. The lone pair on nitrogen will push here. That's how we'll get a double bond. Remove H plus, you will get a imine form. Clear?
Okay. Yes, sir.
Okay, right. Now, this is all what you need to do. Mechanism is the same. So again, O will take H plus from here. These two hydrogens and this oxygen will eventually go. Carbon and
Mm.
nitrogen develops a double bond. So this is what you will get. Imines forming with an R substitution. There is some alkyl substitution or aryl substitution on nitrogen. Then those are
Mm.
called Schiff bases. Clear, beta? So it will form Schiff bases. Any imines or Schiff bases, they can easily be reduced to amines using these reducing agents. Okay. Lithium aluminum hydride, sodium boron hydride,
Mm.
H2 in palladium carbide, nickel hydrogen, ethanol in sodium ethanol, red phosphorus Hi, Clemenson's reduction,
Yeah.
Wolff-Kishner reduction, all of them will reduce that to convert into amines.
Okay.
Okay, right.
Yeah.
Now notice that if you have a ketone, but you are reacting with a secondary amine. In case of secondary amine, what you do? Because now I do not see two hydrogens to remove, right? So instead, you make this ketone into enol form like this. You can make it into enol form. And from the enol form, you can get OH, and there is one hydrogen from the secondary amine. So this hydrogen and this OH can be removed out and then connected. Now what happened? There is a ene group and an amine group. So that's why it is called enamine. Ene plus amine is enamine. So this particular functional group is called enamine.
Mm.
Okay.
Okay.
Next. If at all I have NH2OH group, so NH2, and here this Z group is OH here, then this H2 and carbon will, the oxygen from the double bond will go away, and that will create C double bond NOH. This functional group is called oxime. C double bond N with OH group is called oxime. And usually oximes are colored in nature. Okay, beta?
Okay.
Next, if you have NH2, right, instead of this Z group, we have NH2 here. So that is with NH2, there is one more NH2 group here. So this H2 and oxygen will go, double bond will form here. So you will get C double bond N with NH2. Okay.
Yeah.
So C double bond N, NH2 will be formed here. Okay.
Mm.
Now here, this is when you have NH2, it is called hydrazine. And hydrazine is converting into a product which is called hydrazone. So this is what you got to do. Wherever there is a ine, right, you convert into one. Okay.
Okay.
This is an
Yeah.
ine, hydrazine or hydrazine, convert into one, hydrazone. This will become hydrazone. Clear? Same
Okay.
way, instead of here, if you have NHPH, so with NH2, I have NHPH. Then that is called phenyl hydrazine. So with C double bond O, now it will become C double bond N, NHPH. So what is this one? Phenyl hydrazone. This will become phenyl hydrazone. Similarly, if you have NH, C double bond O, NH2, okay,
Mm.
then this group, I mean from this NH2, this H2 will go away. So I'll get C double bond N with this entire group connected to it. So this is azide. Okay, the name is semi-carbazide. It will become
Mm.
semi-carbazone. Okay.
Okay. Yeah.
Next, with NH2, if you have this group, NH with phenyl and two NO2 groups, then this is called 2,4-dinitrophenyl hydrazine. And this will be the product 2,4-dinitrophenyl hydrazone. Now, this is a very, very important reaction because To detect the aldehydes and ketones, right? This is a test which is used, 2,4-DNP test. Okay. So 2,4-DNP test is a formation of this colored compounds. This is a colored compound. Okay, beta.
Mm.
So if you reduce the temperature, immediately they crystallize into some colored forms. Okay. Usually violet, yellow, red color crystals are formed here. Okay. So that is a detection for the presence of aldehyde and ketones. If you have only ammonia and you have formaldehyde, then it will happen like this. 6 moles of aldehyde, 4 moles of amine will together react to form this compound CH2 6 times N4, known as hexamethyl tetraamine. The common name is urotropine. Okay, this is called urotropine. Urotropine, although I have shown you some mechanism here, it's not essential for you. Correct. I'll just remove this for confusion's sake. Right. So directly check out this way, that wherever there is CH2, that oxygen and two nitrogens hydrogen will go away, and that will connect with CH2. Like that, between every two nitrogen there is one CH2. Got it?
Yeah.
Total 6 carbons and 4 nitrogens. This is a structure. Okay.
Mm.
And this is called urotropine structure. Similarly, if at all I have NH3 and NH3 connected with 2 moles of benzaldehyde, then water from here you can remove, and the other two hydrogens water can also be removed from 1 more mole of formaldehyde, benzaldehyde, and that will create this product. Okay, beta. So
Okay.
if you have ammonia with benzaldehyde, this is the product expected. Similarly, if you have 3 moles of ammonia and 3 moles of formaldehyde, so this is the product that is expected. Okay.
Mm. Yeah.
Next one is Beckmann's rearrangement. What is Beckmann's rearrangement? If you have C double bond O, imagine I react with NH2OH. Okay. You know that it will
Mm.
form an oxime, correct? Just now we learned
Yeah.
this
Yeah.
H2 and O will go away and you'll get double bonded N with OH. Now this could be in a syn form or an anti form. Syn form or anti form means what? This OH and R on the same side. That is called syn uh, uh, syn OH and R group. Now this OH and R dash are trans to each other. So you call it as anti to each other. Okay.
Okay.
Let me show you. If it is coming from an aldehyde, let's say CH3H double bond N and OH, correct? Because it is generated from an aldehyde, it is called aldoxime. And in aldehydes, it's very easy. If H and OH are on the same side, then you call it as syn aldoxime. While if you have H and CH3 here, double bond N with OH, then this is called
And
anti-aldoxime. Okay, so one is syn aldoxime, the other one is anti-aldoxime. So in the
okay.
case of ketones, if you have R and R dash, double bond and NOH, then you need to express which with which group you are making it as syn and aldehyde. So you have to write this as syn. R and OH, these two are syn to each other,
Mm.
and that ketoxime. Or you can also write this as anti R dash and OH ketoxime. Done. I guess you got an idea what we are trying to do, right, beta? Now notice this one. What is Beckmann's rearrangement? Beckmann's rearrangement requires a Lewis acid first. Okay,
Mm.
you can take Lewis acid in any forms. What are the Lewis acids we can take? Check. The Lewis acids which we can recommend here, that includes H plus, BF3, AlCl3, SbCl5, okay, SbF5, correct,
Yeah.
PCl5, PCl3, SoCl2. So you can name it. All of these are Lewis acids. Okay.
Mm. Yeah.
When you have these Lewis acids, right, in the presence of Lewis acid, what would happen? The lone pair from here will get associated with Lewis acid. Okay. As it gets associated, this group will become a better leaving group. Hmm? When it is trying to leave, this R dash group will attack here so that this group can leave. Got it? And as this group leaves here, now what happens? Carbon will gain positive charge on it. Okay.
Mm.
Because R dash group is pushing out here onto the nitrogen side, correct?
Yeah.
So you get a positive charge on carbon. Once you get a positive charge on carbon, water will attack on it. That is the next step, to add water. So as you attack the water here, you will get first an enol form. Enol will convert into this keto form. So what is it ending up as? Amide. It is ending up as amide. And amide on further hydrolysis and heat will convert into amines and acids. Okay, but usually you are supposed to leave this as amides unless this reaction is again given. Okay, product expected is always amides. Okay, beta.
Okay.
Hmm.
Okay.
I'll show you more reactions while solving problems. Okay, Beckman's based problems are a lot of them, correct? So
Mm.
but as of now I'm giving you a basic idea what's happening. Now in Beckman's rearrangement, you cannot expect this, R dash and R are on the basis of migrating aptitude. This migration is only on the basis of the geometry. That is, if OH is going from here, its sigma star orbital will be here. So this R dash will have more access to this compared to this R. Clear, beta? So that's why
Yeah.
the attack will always happen from the opposite group only.
Okay.
Okay. Hmm.
Yeah.
Right. Next, how aldehydes will react with alcohols? Check this out. Okay. See, the reaction type is same. Nucleophilic addition is exactly same what we are doing. पहले इलेक्ट्रोफाइल ऐड हो जाएगा, फिर न्यूक्लियोफाइल ऐड हो जाएगा, या पहले न्यूक्लियोफाइल ऐड होगा, बाद में इलेक्ट्रोफाइल ऐड होगा. There is nothing different other than that. So see, again you have aldehyde, alcohol, but if at all I use water, right, with water generally it is a backward reaction. Okay, because as soon as the water is added, you'll get two OH group. Two OH groups are unstable. It'll
Um,
dehydrate back to aldehydes. But if at all you want to make the reaction more in the forward direction, always use dry HCl. That means without water. Hmm?
yeah.
Now the lone pair from oxygen will take H plus. You'll get OH plus. Then the alcohol R dash OH will attack on carbon. Okay. As it attacks, the pi bond will shift onto oxygen and you will get this product. This product is called hemiacetal. We discussed this before in ethers. We discussed the hydrolysis of ethers there. Okay. So hemiacetal is the compound form. Hemiacetal means one ether group, one alcohol group is present on the same carbon. Hmm?
Mm.
And notice that if you continue to react alcohols again, so lone pair on OH will take H plus, converts into OH2 plus. This is a good leaving group. The second mole of alcohol will attack. So that will end up forming OR dash and OR dash, which we call it as acetal. Done, beta.
Yeah.
So if you take 1 mole of alcohol, you will get hemiacetal. If I take 2 moles of alcohol, I will get acetal.
Okay.
And both acetals or hemiacetals are unstable in acidic medium. They'll immediately react with acids and come back to aldehydes. Okay.
Okay. Yeah.
So you can see hemiacetals are generally unstable in both acidic and basic medium. But acetals are at least stable in basic medium, but unstable in acidic medium. Correct. So suppose if you have ketone, for instance,
Mm.
ketone, when you react with 2 moles of alcohols, you'll get these two sigma bonds to form here and H2O will form here. Correct. Now, what is the problem here, beta? In this reaction, delta H of the reaction. See, usually we know that delta G can be related with delta H. Delta H minus T delta S. Okay.
Mm.
Delta H of the reaction is not very significant. That means it's not highly positive or negative, or, I can say mostly close to zero.
Yeah.
Okay. Since it is not much influential, the spontaneity of this reaction is mainly decided by entropy factors. That is delta S. Okay.
Mm.
Delta S decides whether the reaction will go forward or backward and so. Okay.
Yeah.
Now notice, if you have OR dash and OR dash here, correct? What is the number of moles that are being used earlier? In the reaction, we use 3 moles. Now, how many moles you are getting? 2 moles. So, we can notice that the number of moles are actually reducing. If number of moles are reducing, which means the entropy factor is negative, right, beta?
Yeah.
Right? Reactant के पास ज़्यादा मोल्स है, प्रोडक्ट के reactant के पास ज़्यादा है, प्रोडक्ट के पास कम है, तो entropy overall कम हो रहा है, right?
Mm.
So if entropy decreases, that means it is negative. This negative and negative will become positive. So which means delta G is becoming positive.
Yeah.
So positive means non-spontaneous. Delta G negative means it is spontaneous, correct?
Yeah.
So therefore, this would be more non-spontaneous form. That's why ketones trying to form a acetal is relatively difficult if it is an open ketone. Okay, open
Okay.
ketone means open chain ketone. Hmm?
Mm.
But now I can do one thing. Instead of directly using 2 moles of alcohols, I can use only 1 mole of glycol, because now it has 2 moles of OH group.
Yeah.
So now this O will be removed out with these 2 hydrogens, and these 2 oxygens will get connected here, and you'll get a cyclic structure. Now see what is happening. On the reactant side there are 2 moles, product side there are 2 moles. Okay, so the entropy
Mm.
factor is almost zero. Hmm? But it is giving a cyclic structure. Cyclic structure is always more stable form compared to open structures here, like this. That's why the reaction can start moving in the forward direction. So instead of taking 2 moles of alcohols, if you take glycol, then they can react in ketones and reaction can proceed in the forward direction. Okay? Next.
Okay.
Next, if you have uh, double bond and double bond here, and then you have, glycol given, then what you can do, out of one of these double bonds, whichever is more reactive double bond, here both of them are same, but in generally whichever is more reactive double bond, that
Mm.
is where you will make an acetal, cyclic acetal. The other double bond will be left, correct? Now if the other double bond is left open, that can be reduced by lithium aluminum hydride, sodium boron hydride. Okay, and these two will reduce the keto form into alcohol.
Okay.
Okay, these two will convert into keto alcohol form. And
Mm.
then when you do hydrolysis, this group will go away and you'll get double bond O. Shana, clear beta?
Yeah.
And next, if you have NH2 in the presence of KOH, okay, that is hydrogen in basic medium
Mm.
here. So this group will convert into an alkane, right? Because it is a
Yes.
Wolff-Kishner reduction.
Yeah.
Wolff-Kishner reduction. And once you get an alkane form, then you do hydrolysis, and you know that hydrolysis acetal is unstable. It will get back to keto form here. Okay.
Okay.
So basically, what's happening here is that you are trying to protect one of the aldehyde or a keto group, isn't it? So especially when you are trying to reduce with lithium aluminum hydride. Acha, without using this, if you try to reduce this one, what would happen? Both side will get reduced. Both will become alcoholic forms.
Yeah.
So especially when you want to have a controlled form of aldehyde or a ketone reduction, then this can be used. So
Okay.
acetal formation is specifically used for protecting a group. Right. Next. Up to this part is clear, beta?
Yes, sir.
Right. Okay. Now see the second part of it. The second, I mean, we learned about the chemical physical preparation. I mean, preparation reaction, then chemical reactions. The first part of chemical reactions, which is
Mm.
nucleophilic aromatic, sorry, nucleophilic addition reactions. Okay, all of them were nucleophilic addition reactions. Now, before we go into further different types of reactions, we need to revise ourselves what was tautomerism earlier when you may have learned. Okay,
Yeah.
see, tautomerism is a phenomena where one functional group is interconverting into other functional group. For example, if you have a ketone, if it is in equilibrium with another functional group, which is enol, so then we say it
Mm.
is keto-enol tautomerism. And here we are mainly concerned about keto-enol tautomerism only. We are not worried about the other forms of tautomerism. Okay. And one thing you know that this reaction equilibrium can push into the forward direction if enol content is more stable, correct? So if enol form is more stable, the content can be pushed more in the forward direction. Hmm?
Mm.
And see, when do we have percentage enol as 100%? Now notice this one. In this case, this can be converted into its respective uh, enol form. What is the enol form for this one? The enol form of this ketone is phenol, which is very stable. Stable because of the aromatic ring formation. Second one, if you have pH like this with OH here, double bond here and double bond here and pH. Here there will be hydrogen bonding, as well as here there will be an extended conjugation. So due to multiple factors, even this will also be very, very stable enol form. Okay. Next one, if you have like this O and H here with a double bond and double bond O here, again this will have a strong hydrogen bonding. Got it? That will
Yes, sir.
also make this, for this compound, enol content close to 100%. Clear, beta? So 1, 2, 3, these are all the cases where the enol percentage is almost 100%. Ketone
Mm.
hardly exists. Okay.
Mm.
Next, what are the other examples which have greater than 50% at least? See, if you have a dialdehyde, okay, beta dialdehyde, because these are positioned at beta position here. So these are beta dialdehyde. One
Mm.
keto aldehyde. So this side we have a keto group and this side we have an aldehyde. Or then we have two keto groups. Okay. Now, these cases, right, they all have enol content greater than 50%. And as the bulkiness increases, the percentage amount of enol content decreases. Hmm. But as you go towards beta keto ester and beta diester, you can see this is diester, then the enol content drastically decreases. It goes first to 8% and from there it goes to 10 raised to power of minus 4%.
Mm.
Done. So we can say tautomerism is more easily observed in basic medium as compared to that of acidic medium. Hmm. In basic medium, you can get tautomerism happening more easily. Let me show you how. For example, if you have a ketone here like this, if you use basic medium can easily extract H plus from here, convert into double bond minus, and this minus can be resonance stabilized as double bond here with O minus. This is called enolate ion. So it can form an enolate ion. And then we have this enolate ion. Again, when you react with water here, this will take H plus and convert this into an enol form with OH minus. Then, so enolate ion will convert into an enol form like this. Okay.
Okay.
In basic medium, this is more easier compared to acidic medium.
Mm.
Next, ketones. During tautomerism, instead of using H2O, if at all you use D2O, heavy water. Okay. In that case, at alpha positions, whichever the hydrogens which are present originally, whatever hydrogens are present, they all will get replaced by deuterium. Got it? So
Okay.
it's a part of mechanism itself. Okay.
Huh.
When this happens, I mean, it will take some time, it will take a prolonged time, but all the
Mm.
hydrogens will get replaced. If this happens, we call that as kinetic isotopic effect. That is, any hydrogen getting replaced by deuterium at any position, then we say it is possessing a kinetic isotopic effect. Okay. In short, what does that mean? Suppose if you have a hydrogen here, and let's say you perform a tautomerism here, correct? Or rather, let's
Mm.
say you perform a reaction with HCN. And with HCN, what is the product you will get? We will get OH and cyanide. This is what is the product you should get, correct? And here
Mm.
also you perform a reaction HCN, hmm, correct? So then we have OH and CN here with deuterium, deuterium, deuterium and deuterium. Okay. So if this is the rate constant for this reaction is KH, and here the rate constant is KD, correct? Then what we can say, KH by KD, if the ratio is somewhere greater than 2, then we say it has kinetic isotopic effect. Then we say this particular reaction, if at all this reaction is happening, and this is the problem with the reaction, then we say the reaction possesses kinetic isotopic effect.
Mm.
Just like that, if at all you make a tautomerism, and this forward side tautomerism, the rate constant is Kh. The backward side, the tautomerism is Kd. Okay. Then the ratio of this Kh and Kd, as long as it lies between 2 to 8, then definitely hydrogens will get replaced by deuterium. बिकॉज बैकवर्ड में रिएक्शन बहुत स्लो है, फॉरवर्ड में ही
Yeah.
बहुत फास्ट है. सो किसका कंटेंट रहेगा इवेंचुअली? इवेंचुअली दिस कंटेंट विल बी मोर. गॉट इट?
Yeah.
नाउ notice these examples wherein how many number of deuterium exchanges are happening. Again, this is a standard JE question. Compounds would be given, you're supposed to figure out how many deuteriums are getting exchanged. Whichever hydrogens that can participate in tautomerism, they all will get replaced. See, notice in this case, these two hydrogens can get replaced, correct? Next here, removing this hydrogen will also help. Remove one H plus from here, you get negative charge. That negative charge can go resonance stabilized here like this, correct?
Yeah.
Now during resonance stabilization, check out here what would be the case here. So it could happen like this. We will get this as double bond O with minus charge with double bond. And due to resonance, we can have this as double bond O minus here, correct, with double bond here, correct. So basically minus charge is coming at this position also as well as this position also. Wherever it is coming on a carbon position, whatever the number of hydrogens which are present on that position, you can replace them with deuterium. So that's what I have done. See, these two, and this one. So total answer is 5.
Okay.
Okay, this is
Yeah.
5. Clear?
Mm.
Similarly, if you have this group here, so you can see these two hydrogens can be replaced by deuterium. Minus charge can resonance stabilize. Pi bond will go here, minus will come here. And similarly, minus can come here. Okay.
Yeah.
So total how many can be replaced? 4. Okay. 4 deuteriums can be replaced. In phenolic form, this is given in an enol form. Enol form can be first converted into these keto forms. These two are the keto forms. In fact, these three, this one, this one, this one, all of them are keto forms. So as you start replacing all of them, we know that 1, 2, 3, and this hydrogen can also be replaced by deuterium. So how many we get? 4 of them.
Mm.
So basically, whether you give it in this form, this form, this form, or this form, how many will you will replace? Four. Four deuteriums will be replaced. Okay.
Okay. Yeah.
Next, if you notice this one here, in this case, what would happen? Here we have a double bond. Okay. Now here negative charge will come. Negative charge can get resonance stabilized. Pi bond will shift here. So negative can come here also, na beta. So which means
Okay.
these three, this hydrogen, and these three hydrogens all can be replaced. So answer is 7 for this one. Clear?
Okay.
Similarly, here if you notice, these three are alpha positions, these two are alpha, and these three are alpha. So answer is 8.
Mm.
These many number of deuterium exchanges possible. Okay. If
Yeah.
the tautomerism is not happening, then there is no deuterium exchange happens. Any
Yeah.
doubt?
No, sir.
Right. Okay. So this is the first part of the chemical reactions, beta. Got it?
Mm.
So when it comes to carbonyl compounds, this is the reaction wise. This is the first part which you need to understand. Okay. The second
Okay.
part is all about condensation reactions. That is about removing water, combining two molecules. That includes CaNi0. Then we have aldol and their respective name reactions, various name. This is easy part, but this is the important part as well for both mains
Okay.
and advanced. Clear? So
Yeah.
what I'll do, I'll continue this part the next class. Okay.